good afternoon, everybody. First of all, I would like to thank Director, National Institute of Manufacturing Technology, Ranchi, for extending the invitation to me to speak at this particular conference. So what I'm going to show you today, I'll show you a couple of examples to illustrate how biomaterials and implants are being manufactured in India using some collaborative programs of academia, national labs, clinicians, and industry. Just to give a brief background, this is a human anatomy what I'm showing you. So if you look at from the top part, that is a cranial flap, where for the cranial reconstructions, biometal implants are used to reconstruct the vault and what we call cranioplasty surgery. For dental implants, many elderly patients also receive dental implants for the treatment of edentalism, that is for the partial loss of tooth, natural tooth. Acetabular and total hip replacements and total knee joint replacement, these are the reconstructive surgeries where biomaterials play an important role in the form of a medical device. So what is most important for you to know that more than 80% of the biomaterials and implants used in India are all imported from Western countries, including North America as well as Europe. So what is another important thing for you to notice, then in manufacturing these particular biomaterials and implants, some of the major things which are of relevance is the design of the implants, which can be either patient-specific or which can be either standard designs which are used for dental implants. As I said, the patient specificity is more important for example, cranioplasty surgery, biocompatibility, and last one is the implant quality validation. And that needs to be done in a regulatory body compliant certified facilities. So Indian government recently announced a medical devices policy. Currently, Indian medical devices market is 90,000 crore or 11 billion US dollar, and it is expected to increase up to 50 billion US dollar. So Cabinet has approved the following policy for the medical devices, and that is for the 6 strategies, and particularly and there is also implementation action plan which essentially will foster biomaterials and implants in India. One of the major thing that has been emphasized in this policy is the indigenous manufacturing of high quality biomaterials and implants right in our country in India. Now if you look at that biomaterials research in India, in the north, east, south and west, there are a large number of research groups, individual research groups. They have been working in this field and mostly pursuing what we call biomaterial science. However, there are some institutes like Sri Chitra Institute of Medical Science and Technology down south in Trivandrum, or Translational Health Science and Technology Institute in Faridabad in the north. They have been working more on the translational research, taking the technology to directly to the patient's bedside. And some of the new initiatives is that hospitals and postgraduate medical schools in academic university campuses like IIT Kharagpur, they have started an MBBS program, and they have a hospital. IIT Kanpur is going to start the Langwal Medical School, and IISc Bangalore is going to have in 2024 Bagchi Parthsarathi Hospital that has an 800-bedded hospital, and essentially that will accelerate the innovation to directly deployment in the area of biomedical devices and systems, precision medicine, and digital health. So these are some of the theme areas. So having considered this particular background, I would like to focus on 3 different examples. One is the polymethyl methacrylate bone flap from cranioplasty surgery. This is an example of the personalized treatment or more patient-specific surgeries. Orthopedic and dental implants, that is more useful for public health care because these are available, these implants needs to be available to the surgeons in standard sizes. Then future scope I would like to highlight is the data science for implant manufacturing and translational ecosystem and its potential impact. Let me introduce you to the translational research in the context of the healthcare or biomedical engineering or based on biomaterials and implants. So if you look at this particular tetrahedron, because being a metallurgist or material scientist, we are very much used to this kind of tetrahedron because what we call process microstructure property performance correlation. So similarly, what I say, the lab scale development, it goes to the design and pilot scale manufacturing, and post-manufacturing implant quality validation, and subsequently it will have an impact not only on personalized treatment but also on public healthcare and digital healthcare. Some of the boxes that actually allow you to understand what I mean by lab scale development going to transition to the design and pilot scale manufacturing in terms of developing or innovating new design concepts, biomechanical validation, biocompatibility analysis. When it goes to pilot scale manufacturing, it is more test batch production, manufacturing scalability. When it goes from post-manufacturing implant quality, then implant testing must be done in certified labs, and that are essentially required for getting regulatory approval, sterilization and packaging. And we need to involve clinicians because they will help us in the clinical study design, and they will essentially do the final clinical study with our inputs in terms, and then subsequently clinical outcome analysis. Right, so this is the broad objective of my presentation. It is design and manufacture biometal implants for both maxillofacial and musculoskeletal reconstruction applications. And when I say in an emerging translational ecosystem, Professor Amitav Ghosh and other speakers in the morning, he said this translational research is slowly emerging in India. So we need to bring together industry, we need to bring together clinicians, and we need to bring together academicians as well as the data scientists in the same platform. And what we employ the engineering design approaches, experimental and computational biomechanical analysis. In terms of advanced manufacturing, for the dental implants, we use 9-axis CNC machine and metal 3D printing, biocompatibility assessment, and finally data science approaches for accelerated development. So just to give you first example, in the polymethyl methacrylate bone flaps or cranioplasty surgery, when a patient has undergone a stroke or road traffic accident, which is fairly common in Indian roads, or brain tumor, so the part of the brain or part of the cranial area is being depressed, and that actually compromises the neurological functionality of a patient. Now, to restore the neurological functionality, the patient has to go for decompressive craniectomy. So if you look at this particular area, this is the defect area, and first we need to have the CT scan of the patients, and with this CT scan we need to I just need to first explain the concept. So if you have the 3D CT scan image, so then we need to consider the front view, back view, lateral view, and superior view. All the different views are to be carefully considered, and that will allow us to precisely delineate this particular defect morphology, not only in terms of the size, but also thickness of the bone flap that is required to reconstruct this particular cranial flaps. And what we do, we first do all these engineering design approaches, then we 3D print the human cranial model, and on that particular cranial model, we cast the polymethyl methacrylate as you see here, and then we have to intentionally cause some small holes in that for the cerebrospinal fluid to be transferred between the outside of the flaps and the inside of the flaps, and then it has to be implanted into the patients. Now, to take up this study, we have brought together neurosurgeons from two different hospitals. One is the Ramaya Medical College that is next door to IISc, and one is the Datta Meg Institute of Medical Sciences and Technology that is in the central part of India near Nagpur in a place called Wardha. And these other clinicians, Dr. Manish Baltia from Jaslok Hospital in Mumbai, so he was also involved as part of this team. And then we have gone through all the ethical clearances both from Indian Institute of Science as well as the hospitals, and this was the inclusion criteria of the patients. So patients between the age of 18 and 70 who underwent decompressive craniectomy for trauma or stroke, they were essentially recruited in this particular study, and some of the patients like pregnant women or patients with previous infection at the operative site, they were excluded. And this essentially gives you, this is the pre-operative views of the patients, and then you can see that how much is the deep is the skull. So these are just to show some of the male and female patients that we have recruited, and the same patients, the post-operative view, you can see that within about 2 years, from 3 months to 6 months, this skull has been reconstructed after the cranioplasty surgery. So there is a movie here, and you can see that when a patient is undergoing in the operation theater, and the neurosurgeons, or craniomaxillofacial surgeons, they are essentially putting the polymethyl methacrylate flap, and there is, if I go further in the video, you can see that so this is the cranial. Oops. So in the operation theater, when the patient is full body anesthesia, they open that cranial area, defected area, and now they are putting these polymethyl methacrylate bone flap, and then they are also using the titanium screws and micro screws just to place and fix these bone flap at the defective sites. So the table essentially shows you that what is the typical bone defect area, and if you look at the defect area, we can reconstruct the defect area up to 175 centimeters square. So there are several clinical outcome analyses we always use, that is the Glasgow outcome score or Glasgow coma score, and that essentially indicates whether the patient has regained the neurological functionality at during the post-operative period. Okay, so this is the summary of this part of this cranioplasty work. So what I've shown you that we use the several engineering design softwares to essentially delineate and define the morphological defect, morphology of the cranial defect, and subsequently we, during this the intraoperative images where we place the polymethyl methacrylate bone flap, and then post-operatively we have found out that this is the case for the 57-year-old male patients where 116 centimeter square defect was reconstructed, and this is the case for 32-year-old female, and where this around 140 centimeter square defect was reconstructed. So this right-hand panel, what you see here, CT scan analysis of the pre-operative, and you can see this is the cranial flaps defect size, and post-operative you can see that it is being correctly reconstructed. What you notice here, that in the pre-operative cerebrospinal fluid is little bit squeezed or compromised. Post-operative cerebrospinal fluid has regained its original shape in terms of filling up this volume. So now let me move into the orthopedic implants, as I said, which are largely used for public health care, and these are to be available in standard sizes. So if you look at this particular movie here, so this is the total hip replacement surgery, and typically many patients, many elderly patients, and wherever it is more challenging because many elderly patients have bone loss or osteoporotic bone, that means the bone density is less, and when we are placing this total hip joint replacement, which is an acetabulum, and also there is a stem part in it. So essentially, it will allow the patients to regain its original mobility, not to the extent as an adult, but also to their regular activity and so on. So what happens in this orthopedic surgery also, all the implant and devices, they are essentially imported from United States, North America, or European countries. So there are two types of orthopedic surgeries, particularly hip surgeries are possible. One is the cemented hip surgery, to cemented total hip replacement, surgery, or non-cemented or uncemented total hip replacement surgery. In case of cemented, we use polymethyl methacrylate as the bone cement, and it is mostly used in the elderly patients, or particularly osteoporotic bone. So what I'm going to focus in next 5 to 10 minutes is that what we have developed acetabular liner, which is ultra-hemocrat polyethylene. So there is a standard practice, or this is the manufacturing route, has been used for quite some time in the industry, and that is based on machining. But we, with the help of NIAMT Private Limited, we have introduced a new manufacturing technique which was not used for the acetabular liner manufacturing, and that is the injection molding. So again, we brought together our manufacturing team as well as the industry collaborators. This is Orthotech India Private Limited. They are the implant manufacturers, particularly hip replacement devices. They are based in Gujarat. And so this manufacturing company also has its footprint in United States as well as in Europe, and Orthotech India Private Limited, they also sell their devices not only in India but also many African countries. Now, conventional manufacturing, you take the USFP powder, then you do gamma cross-linking, annealing, extruded rod, then you machine. Machining also involves a lot of material losses, and many times there are some machining marks which are left behind on these particular surfaces of the finished product. Now, in the injection molding case, what we have done in the lab scale, we have used plunger-based injection molding at IISc. Then subsequently, when you transfer that manufacturing process to the NIAMT Private Limited, what we are trying to do screw-based injection molding. And in screw-based, there is a compression ratio of the screw that is important because that gives a particular shear. Now here in the ultramolecular polyethylene, as many of you may be knowing, that it has a very high molecular weight, and what it means that higher the molecular weight, more is the viscosity, and more difficult is the manufacturability. But at the same time, UHNWP has very high properties in terms of strain and also elongation to failure. So challenge was to retain that strain ductility combination, at the same time establish the manufacturability of the UHNWP, which was not tried before, using this particular injection molding as the route. So we have learned a number of lessons in our way to establish this particular technology. I'm going to show you some of the results here. To start with, we have used the GUR 1050 grade, that is the medical grade UHNWP, and that is the grade that all the orthopedic implant manufacturers also use when they use the machine, the feedstock or extruded rods to make this UHNWP acetabular liner. So as I said before, that from the more processing point of view, it is the combination of the L by D ratio here in the screw-based injection molding, and also CR, that is the compression ratio, that is feed joint channel depth to meter joint channel depth. These two are very important because that decides the shear that the UHNWP feedstock that will be experiencing. So UHNWP as such, very difficult to mold otherwise. So what we have done, we have essentially modified, but when we modify to a very minimal extent because otherwise biocompatibility and strain ductility combinations will be compromised. So what we have done, we have used the polyethylene short chain, and this will be wrapped on the malic anhydride, and when this short chain polyethylene is dispersed in the ultra-mounted polyethylene, that used as a viscosity modifier. So that reduces the viscosity to certain extent, which allows the UHNWP to be molded in a particular injection molding route. And if you see that signature, that viscosity also is reduced, and that also impacts the mechanical properties. If you see that this is the typical tensile stress strain plot, where up to 5% NP, that modified polyethylene addition, we can get up to 800 to 1000% elongation to failure. That is a very high value in the case of the thermoplastic polymer like UHNWP. So subsequently, we have done all the conventional materials, the characterization analysis, like particularly differential scanning calorimetry, to see whether this melting range is compromised, or rheological analysis. This is the parallel plate rheometer that we have used, where we can see that there is a clear indication by addition of this polyethylene, short polyethylene chain, by dispersing the ultra-molded polyethylene, you can significantly reduce the complex viscosity, not only in the temperature sweep, but also to substantially in case of angular frequency. Please note that the scale, Y scale, is in the log scale here. Now, this gamma radiation is another important thing that we have to understand, that whether this gamma radiation for the cross-linking purpose, which is used at ultra-molded polyethylene, will that have some impact on the properties of the ultra-molded polyethylene. Now, if you look at it, this delta epsilon value is essentially change in the strain to failure, which is a measure of the ductility divided by the non-exposed ultra-molded polyethylene. So essentially, it is a measure of how much change in the strain to failure is increased due to the gamma cross-linking, and you can see that the significant increase in the strain to failure because of the gamma cross-linking. We try to understand that what is the changes and how gamma radiation essentially introduces the free radicals, and which will help in the H crosslink and gamma crosslink there, and that will have an important impact on these particular properties. When we have done injection molding, this is the tensile sample, some parts of the tensile sample, we did not find in the presence of any defect like blowholes or other type of defects when you have done X-ray based analysis. Now moving further, when you use the different combination of the processing parameters like melt temperature, and by keeping the melt temperature constant, essentially we have found that there is a range of tensile strength we can obtain. And we are trying to understand that what is the underlying parameter which will have impact on the ultimate tensile strength. We found out the residual stress in the polymer, which may be fairly small compared to that in the metal, but this residual stress also changes from 0.5 to 1.1 MPa, and ultimate tensile strength scales more or less linearly with that of the residual stress. So we are trying to do more synchrotron analysis, trying to understand what the nature and magnitude of the residual stress and its impact on the ultimate tensile strength. So when we do this, all this materials development, we generate a lot of data. So we also use some of the machine learning algorithms like categorical boosting, for example. Here it is being trained on the residual ultimate tensile strength. So this is the actual values training data, and this is also the predicted values, and we get that RMSE, that is the root mean square error, is 3.03, but the R square value is 0.91. So anything above 0.95 and 0.99, it is a fairly good correlated or predictive about good prediction according to the machine learning models. So now when we essentially establishing the injection molding, we are trying to use several softwares. That's one of these mold flow, and these softwares allows us to use this particular moldex here. It was allowed us to use that how this UHNOP material is going to fill the mold cavity, what is the time scale through which these particular filling operations will be completed, and what is the force, the clamping force it is needed. So this kind of computation analysis also allows us to predict that what could be the packing time and what is the melt front temperature. From the materials perspective, we also have to measure PVT value of this particular ultra-mold polyethylene and also mold shrinkage factor. All these combination of these parameters as well as the mold, as well as the computation analysis of the melt flow to the injection mold, that was required, and subsequently we are able to manufacture this particular acetopolymere liner, which is of different sizes, as I said before, outer diameter 52, inner diameter 32 or 28 diameter. And then we have designed multi-cavity mold so that number of acetopolymere liner can be produced in less than 2 minutes time. So when we did this acetopolymere liner using this injection molding, we had to introduce some changes in the acetopolymere liner design itself. Anytime we change certain design in any implant, we need to validate using biomechanical analysis like finite element analysis, whether those changes will not compromise the biomechanics. And in this particular case, since it's orthopedic implant, we use the human walking cycle. Here, it is the different phases of the walking gait. And in the different gait cycles, we have to calculate that what is the von Mises stress in the implant and what is the strain in the periprosthetic bone. And if the strain value is in the region of 2000 to 3000 microstrain, this is the bone remodeling is likely to take place. And that is what we need in our implant also. So this is the standard finite element analysis we have used. We have also defined the meshing criteria and mesh convergence criteria before arriving at the computation biomechanical analysis. We have used the different subject weight, like from 55 kg to almost 85, 95 kg, 100 kg subject weight, and there we have used that what is the stresses, von Mises stresses that will be generated at the acetopolymere liner wall as well as around the different parts of this acetopolymere liner. We have seen, we have recorded some kind of stress concentration at some of the edges. Now, in terms of the magnitude, if you see von Mises stresses that will be generated, which is in the LC2, that is the highest, which can go up to 25 to 30 megapascal. So we have used certain particular criteria for the von Mises stresses in terms of the percentage nodes in the region of interest. And if you look at this percentage nodes in the region of interest, 400 to 5,000 microstate, which is very suitable for the bone remodeling, we have found out that it increases with the more subject weight. That means heavier the subject weight, more likely the bone remodeling will take place after the implantation. So this is all about the computational biomechanics. We have used the hip simulator testing facility at CGCRI Calcutta, and we have done that acetabular liner and then implant, that is the fatigue wear study. That is also being complemented with a dynamic finite element analysis, where we can show that as the number of millions of cycles will progress in the walking gait cycle, how the deformation will generate, and then subsequently we can correlate with that of the gravimetric weight loss that the material is going to experience. So this is the CGCRI, the hip simulator study, but this is not perhaps the state of the art, because it's only 3-axis movement. But what is more important, this will allow us to screen these materials further. And currently we are doing the same hip simulator study at the ISO certified lab, RMS Foundation in Switzerland. Now biocompatibility is also important, and biocompatibility essentially means compatibility of the materials with the key components of the living system. What it means, key components like cells, genotoxicity, DNA, RBC, red blood cells, platelets, that is essentially define the blood compatibility, and tissue compatibility, what we call the histocompatibility or osseointegration. So we have used different type of cells like osteoblast cells, that is bone cells, and myoblast cells, that is muscle cells. In all these cases, we have found that over the period, cell numbers will increase, and therefore these materials are more cytocompatible. Genotoxicity is very important. Whether these debris particles, when are leached into the living system, whether it is going to break the DNA, double-strand DNA, and that we have quantified using that in vitro genotoxicity assessment. Then we have used that rabbit blood to find out that whether this platelet has been destructed, and finally in the rabbit implantation we have done up to the 12 weeks, and then we did not see any signature of the acute inflammation or any kind of negative impact of the materials on the tissue level compatibility. So what are the lessons that we have learned? That injection molding as a scalable manufacturing route, then close control over the UHMD modification that allows us to control residual stress, and that also essentially helps us to establish that acceptable dimensional tolerance, and design changes in the cemented acetabular liner essentially helps in the bone remodeling, as also do not compromise on the fatigue wear. So last example with dental implants, perhaps I will not go into any details, but just quickly go through a few slides. Now dental implants, these are 3-piece dental implants. We have essentially implant which goes into the mandible, and then on the top of this dental implant there will be abutment, and then on the top we'll put the prosthesis of the crown. And in this is a two-step surgery. So one of the major thing that I have mentioned, that most of the dental implants are all imported from abroad, and if you look at the sum of the price, this is exorbitantly high, and that cannot be essentially so that many poorer people in this country cannot afford to go for this dental implantation at this price. So again, we have brought together our manufacturing team from Orca Medical Devices Private Limited, then Trustin Analytical, 3 clinical collaborators from KGMU Lucknow, Ramaiah as well as DMIMS, and then we have used this particularly innovate this dental implant. And if you look at this implant, what we call hybrid threaded morphology, a different region from collar region, the thread is very deep, and middle region thread is less deep, and the collar region it is a more buttress thread and or micro V threads. So they have certain clinical applications of all this thread morphology, and what we have done, we have kept that middle to active ratio is the constant, and collar length is set to 3 mm. Initial trials were done at CMTI Bangalore, and subsequently test batch and production manufacturing batch was done using the 9-axis CNC machine at Orca Medical Devices, Hyderabad. And here again, when we go into design conceptualization to manufacturing scalability, we had to introduce several changes in the process just to show you that what are the different design changes that we have introduced, and then what are the different diameter from 3.7 millimeter diameter to 5.5 millimeter diameter, and different length. So these are the standard length of diameter, length to diameter dimensions of dental implants that must be available to any prosthodontist for the dental surgery. And these are now ready, and this has gone into the clinical trials. So this, we have done some biocompatibility analysis. There is Straumann implants which are made from Switzerland, and then this is the IISc implant. We have seen in our implants, because of the thread morphology, it is engaging more bone after 12 weeks in the rabbit condyle when it is being placed. So I think I'll just move to the last things. That is, I'll just, because of the time, that I'm not going to show any details, but just to show metal 3D printing some examples. So these are the different implants which are used in the neurosurgical applications. And you notice that in different applications, there are struts of different thickness, and the way the struts are also placed in the interpenetrating manner, that are also different. So this kind of integrated structure by conventional machining is fairly impossible, and therefore that what we are producing, we are doing the metal 3D printing, particularly laser powder-based fusion processes, where we are building, where we are designing to different strut sizes as well as strut thickness, and then subsequently we have done a lot of single track experiments in LPBF experiments, and we have established the printability map using different laser power and then velocity combinations. And based on these, we have produced the what we call the decision, what we just go to the last slide. So what we call the decision data-driven modeling supported decision support system. So if an implant manufacturer will ask you that what is the strut thickness, and then if you keep the strut thickness as an input dimension, the output will be the processing parameter, so that all this trial and error based experimental process can be avoided. This particular approach has been transferred to Orthotech India Private Limited, and they are now essentially manufacturing acetabular liners of different designs, as well as the implants for the neurosurgical applications. So this is the impact of our translational research in the field so far. One is the cranioplasty surgery, dental implants, acetabular liner. What I have not shown you in this study, that our group has worked for last 15 years on the regenerative bioelectronics, essentially guiding the stem cells through different lineages, either to bone cells or to cardiac cells or to neural cells, when these stem cells are being cultured under the influence of external electric field stimulation. And this has actually, we have not only done experiments, but we have also done a lot of computational analysis to find out what are the stresses that the cells will essentially experience, and how the stem cell guidance can take place under the bioelectric stresses in general. So Tata Steel has started a new business vertical called Medical Materials and Devices in 2017. I have been guiding the Tata Steel Medical Materials R&D team, as well as the Ceramic Private Limited. That is one of the company that has come out of this, that has come out over the last 7 years. So this is the total translational ecosystem that we currently have. It is emerging, and that is going to have more impact in the days to come. I would like to acknowledge several students who have graduated from my group, as well as my family and parents. Professor Amitabh Ghosh knows my parents also. Different government sponsors, private sponsors, and thank you very much for your kind attention.
Very energetic and inspiring talk indeed, and definitely something that India could make major progress towards manufacturing in the country. Any questions, please, for Professor Basu? I had one, but I want to wait for everyone in the audience. Yes.
So actually, in the 3 implants you shown, the teeth implant, if the teeth implant is gone, the bone in the teeth implant will, in the place of implant, the bone will regrow. And in the joint bones, you said, it also grows in some cases. In the skull implant, we can see some patients have some cases blood comes out after the surgery. So in this, to be specific, brain hemorrhage is a thing where we can see. So in this three things, I find a thing common where we. Is there any person who come up with an idea to maintain the healthiness after these implants and all?
No, but I mean,
I think I haven't made the questions
Post-operative measures.
Post-operative measures, essentially that is called clinical outcome analysis. And clinical outcome analysis are very different depending on what kind of surgery the patient is. For the cranioplasty surgery, the post-operative outcome, people use Glasgow outcome score or Glasgow coma score. So Glasgow coma score, if you look at it, there is something like eye opening or walking or this kind of performance, regular performance or any neurological malfunctionality. So those kind of things are being assessed. But as for dental surgery, whether the patient actually regains that original masticatory functions, like chewing, for example, or whether there is a bone growth and this bone has been integrated or osseointegration of the implants. So all those things are being measured by CBCT, bone beam computed tomography analysis and so on. So depending on what kind of surgery the patient comes, the post-operative outcome analysis or clinical outcome analysis, they are also different.
So much is being done on biomaterials. Why not much what we find in the area of cartilages,
Yes.
regrowing cartilages and their replacement? Why it's not there at all?
Yes, actually very good question, and many orthopedic surgeons have asked me the same question. So cartilage is the one thing, these cartilage cells, the chondrocyte cells, that is the which constitute the cartilage, and that growth of this cartilage, and there is a 3-layer structure there in the cartilage, bone and cartilage interface. There has been tissue engineered products, not this kind of hard materials like titanium or ultramicron polyethylene, these soft materials. There is some preclinical successes there, but those materials has not been tested in the human patients, and this cartilage repair remains a major challenge.
So what is the duration of this replaced hip, like in TKR, like total knee replacement? We have seen that in 2016 my father undergone TKR. So there we came to know that lifespan of that new joint is around 25 to 30 years.
Not that much, 15 to 20 years, yeah.
Right. So nowadays the hip replacement that you were talking about, what is the time frame? Like suppose at my age of 40, if I need to go through an accident and I need to go through hip replacement, how long will it last?
It is little longer than knee, because the knee actually it takes almost all the body weight. But that hip case, it is kind of 20-25 years. So if a younger patient, it is more likely the patient might have to undergo revision surgery. Revision surgery means either femoral head or acetabular liner. If they worn out and it causes a lot of pain, then again patient has to undergo surgery. So what I am showing you that biomechanical analysis, where not only computational but also experimental, this validation is very important, because that actually allows you to predict that what could be the expected life of the implant.
Thank you.
Ravi.
We will have to take the last question from Ravi Shankar.
So, from the Indo-MIM, you said that injection molding you do. Is it the final step, or you need to do some post-processing also?
Post-processing means gamma processing.
So, surface and everything?
No. All of that.
Very good. Let's thank our speaker again and welcome our next speaker. Our next speaker is Shiv Kapoor, University of Illinois, very well known both in India and in the United States and worldwide for his work on advanced manufacturing techniques.
Good afternoon. This is going to be a little different talk. This work is based on the sponsored work from Intel Corporation. So Intel, as you know, is manufacturer of a lot of chips and electronic manufacturing as such, and they have plants all over the world. And the problem they have is that when all these components are assembled, they test every part and they find out if there is a defect, then they want to know where this defect is started. So it is very hard. Each plant is monitoring their own quality for the product, but when things come together, it becomes harder. Similarly, if you think about even in a single plant, you have different operations, different process stages, and the fault can occur any time, but eventually it will show up in the product quality. So this talk was based on, you can not only tell when the product is found faulty, where this will occur. Most of the techniques which we have seen over the years is that they can diagnose the problem that there is a fault. But what is the source of the fault? That is a big issue and very haunting issue for manufacturers. So this work was done on basically trying to develop an approach where you can not only monitor the process but also diagnose the root causes, and not only root causes but also tell when it actually and where it has happened. So it's and it's mostly, as you'll see, it is data-driven approach, and the work which I'm going to present is essentially Bayesian network. Bayesian network has been there in the past for a long time, but in this context, as you will see, looks at it in a different way where you can utilize today's machine learning technique, which is one of the Bayesian network, and the root cause diagnosis. This is a picture Mark can recognize coming from his book on multi-stage manufacturing for flat panel. But the idea here is that this is a multi-stage manufacturing process where different stages, different steps are involved in making this flat panel. So the idea is, what is multi-stage manufacturing? Where a number of independent components come together and it makes a complex manufacturing process. And the challenges with this problem is that, as you can see in this picture here, now I flip it earlier, that different stages are coming in there, and output of one stage becomes input of the second stage, and so on. And each stage has its own input and process parameter. And if there is any problem in one stage, an output could be affected in a way that it can also affect eventually the final product. So the idea is that changes in one input stage causes variation in the output, and output variation flow into the downstream as input. And our goal is, how do we really predict where it happened, and then how we impact this product failure. So, as I said here, a lot of things happening now these days about data analytics, machine learning, artificial intelligence, you hear a lot. But we also are collecting a lot of data because of fast computers we have, a lot of sensors we can put in. So a lot of data is available to us. Question is, how do we utilize this thing? So this approach, as you see, kind of takes into advantage of this particular data collection which we have. Now, root causes, so there are two problems which I'm going to talk about. One is process monitoring, and another one is root cause diagnosis. Monitoring is usually done with a conventional control chart. Those who have been exposed to statistical process control or shared control chart, essentially the idea is that you monitor certain characteristics of the output, and you continuously monitor it, and then you will see that sometimes Where is the cursor? Oh, here. So here, as you can see that you are monitoring the output, and there are these lines which you see, these are like limits, where if the performance, anything goes outside the limit, you say the product is faulty. Something has happened in the process. Process is not behaving normally. So that's usually the control chart approach, and in most of the industries, they will follow this type of process. Now the problem is that they can only tell there is a problem, there is a fault, but where it has happened, they cannot predict. So diagnosing the problem is what one of the conventional approaches will not be able to solve it. Now, diagnosis problem can also be done with the modeling approach. This is one of the approaches which has been used successfully in auto industry, where they have a lot of assembly operations, and they use state space approach, where they model these different inputs to the stage and the output and so on with a simple linear relationship. Now, of course, to model this, you need to use some physics-based knowledge, which is very good in terms of understanding the system. But there are a lot of assumptions made. As well as the assumptions is usually what we call linearization and normality assumptions. But if the model is not accurately done, the root cause diagnosis becomes a problem. That's one of the approaches. And then secondly, when it is a complex manufacturing process, there are a lot of stages involved, this modeling approach has some limitations in this case. So here again, it requires a lot of time and effort to do this model-based approach with root diagnosis. And still, there is a problem in terms of, accurately modeling the system. The other one is what is being done today, a lot of data-driven approaches. You collect a lot of data, and then you can use machine learning, and you can diagnose the problem. You can try to diagnose the problem in terms of what has happened. You recognize the patterns. For example, you study, input-output relationship, and then you try to diagnose that. So the idea here is that these kind of models are good in terms of trying to tell what the problem is, but they are lacking the physics, underlying physics. So, there are some limitations, and as you see in literature, and I've been, editor of a journal for some time now, and I see a number of papers coming in, artificial intelligence, machine learning, tremendously using these data-driven approaches. But again, there are problems when you have multi-stage manufacturing process. Single stage, you can deal with these things. Multi-stage, a lot more challenges. So, in summary, if I try to say where we stand today in terms of root cause diagnosis problem, that there are control charts for monitoring. Most of the time, these approaches are good for single stage. When you have a complex multi-stage problem, there is an issue with the diagnosis. So what we are trying to propose here is, so our objective for this project with Intel was to, unified approach to diagnose the problem for monitoring and diagnosis, and of course it's implementable. Intel is not going to sponsor a research project which is purely research and published paper. They want to implement it. So the idea was that approach should be simple enough and it should be implementable on a factory floor. So that was the goal for this project. And as I said earlier, that when you talk about root cause diagnosis, the idea is to try to identify the nature and occurrence when fault has occurred in the system. Now, when we try to say root cause diagnosis, what is the problem really? What do we mean by root cause diagnosis? So this is a simple representation of a multi-stage system, as you can see, from the stage 1 to stage n. And the idea is that you have each stage has its own input, process parameters, and of course there is also a noise factor coming into play. So we divided these two inputs here. One is basically the input to the system For example, in the manufacturing case, you are machining something, you will have a raw material, that's the input. Then you have a machine parameters, and that is what we are setting as the process settings. And then there's an output Y here. So as you can see here, there are two kind of inputs. One is X, represented by simple input to the system. S is basically process parameters, and the Y is response. And what we say in a normal system, if everything is behaving right, product is acceptable quality, then we say that these inputs follow a certain distribution with, here in this case, simplistic case, we assume normal distribution with certain mean and certain sigma values. And same thing with this. And our thinking is that if the process is behaving normal, the Y, which is the output of the process, will also be normal, if everything is correct. So now, as I said earlier, that Y is what we are monitoring all the time for product quality. But our interest is to diagnose the problem. That means where in the input the change has taken place. Or if X is normal and if something has happened, it becomes abnormal, can be diagnosed as problem. So the idea is to develop a map not from Y, which is a function of X and S, but the other way around, that what would be, if we monitor Y, what would be the, values of X and S, which is input. So that's what we're trying to look at the map, between X and S as a function of Y. First problem. It is easy to monitor Y, which we observe, but what we are trying to predict unobserved, which are something which we don't monitor, X and S. So how do we infer X and S? And that's where we use Bayesian approach. Okay, it's a probabilistic approach, and the idea is that we can, based on monitoring Y, which is what we can observe in this process, we can essentially tell basically what's happened to the inputs, X. And if we can develop the inputs offline, we can tell where the fault has taken place. So that's the concept. Bayesian network approach. Here we're trying to use this. If you look at the right hand side, what we are saying is that it's a probabilistic approach where it says that if Y is, and what I have done here is kind of two states, like a product is good or bad. Just two outcomes for the simplicity. So what we are saying is that if the output is high, for example, which we observe, okay, given that input is also high, what is the probability of that? So we can see clearly, as in this chart, there are four combinations. Probability of Y is high, or probability Y is low, or probability Y is high when X is low, and probability Y is low when X is low. So these four combinations, 2 and 2, gives you all probability. And you develop basically this concept of probability and develop a network, a Bayesian network, for collecting the stages in a Bayesian network model. Let's see here. So the concept here is that first we take the process, multi-stage process, and we develop a flow of Bayesian network. And I'll show you a simple example how network is built. And then once we have a Bayesian network, based on the Bayesian probability, we can predict the state of X inputs. And then we monitor X instead of just Y. And if we can monitor X, we will know when X became abnormal. And then we know the fault has taken in that input. So with this example, you will be able to see exactly what is happening. So we will make the control chart just like we have been doing for Y, for observed value. But in this case, using the Bayesian approach, we will be able to get the control chart on input so that we can diagnose the problem easily. So here, one thing which I want to make clear about, in summary, there are two color inputs and outputs. So, and I say unobserved and observed. What does this mean? That in a factory floor, usually for the product qualities, whatever measure you take, you observe Y, but you don't observe X. And X is the input to the stage. So if there is anything fault in X happen, okay, that's what we are trying to predict based on the observed value of Y. So these are observed and observed input. And what we're trying to do is not only observe this Y, but we, using the Bayesian approach, we will find these values of X, and then we monitor X and try to diagnose the problem. So my basic steps of methodology, modeling and inferencing. That means we identify and establish variable, generate the Bayesian network, and then train the Bayesian network. Just like any AI technique or machine learning. Then we develop the control chart. Control chart are done on the input, which are coming out of the Bayesian network, probabilistic nature. And the third thing is that once we have that control chart, we have to establish some criteria when we say that input is gone out of control. So let's just see how what I have talked so far works. A very simple example of making, say for example, in a bar you turn and then you have a keyway, broach keyway. So it's a two-stage process. One is just machining, turning, and you create the two diameters, step diameter, and then in the second one you put the broach in the keyway. So there will be two-stage process in that sense. Now each stage, as you can see, that in the station 1 when you are doing the machining or turning, you have material as an input, and then you have essentially some machine parameter which will be S1. And then you inspect this, say like surface finish or something like that, an output, Y. And then you go and take, say like larger diameter bar, and you have a broaching operation where you have again some additional process parameter, and then you inspect eventually some characteristics of the keyway which you made. Based on this idea of these two states, you build a network. And what you see here is the full network where you have input x1 and s1, and then you have output y11. As you can see, y1 is dependent upon input x11 and s11. Similarly, another output after stage 1, we call it y12, and it's also function of these two inputs. And then this input goes to the second stage, output, and then some additional input coming into this. And you go this way, and it's a full Bayesian network. Now, if you imagine that you've got 30 stages, this network becomes very complicated, very difficult to predict. So one thing you have to do is to simplify the network. So our contribution to the Intel project, because they have really complex manufacturing process, a lot of stages. So the idea was that how you simplify this network so that it is manageable in terms of predicting, developing the probabilities. So here we use this structured learning algorithm, and we try to use some basic knowledge. A lot of times what happens on the factory floor, when they are monitoring quality, a lot of experience comes into play. People who have been working there, they know, oh, this is wrong, it might have happened because of this. So that knowledge is there. That knowledge we can use in actually reducing the complexity of the Bayesian network. So that's one of the approach people have done. And then there are some constraints which you can use. So combining expert knowledge with data-driven learning, and some of these expert knowledge like failure mode and effect analysis or hierarchical variable ordering, these are the kind of things which can be used to simplify. So in this approach, we try to use this idea of pure data-driven approaches, plus adding some of these knowledge-based sources to simplify Bayesian network. So we did this work a little bit and try to, use these two methods. One is FMEA and then hierarchical variable learning process, and try to study that how Bayesian network behave when you add these knowledges. So in this case, for example, there are 4 networks. You can see simple data-driven hill climb approach. Then we added FEMA knowledge. Then we added the hierarchical learning knowledge, and then we added both of them with the basic one and makes this thing. And we found out that, of course, if you add the knowledge, the Bayesian network prediction is much better because you added really some information which you know a priori. So with this idea, we worked on it and then we tried to optimize this process. And after optimization, the idea is that your network, which was not complicated, reduces. Okay? And once we have this, now the question is that how do we develop the probability structure so that based on the output, how do we go back to the input? This particular slide is just showing this idea of discretization of the input and the probabilistic nature. So this particular, Bayesian network which we just formed, then we developed, which I told you earlier about that we have to do learning, of the Bayesian network. Then we need some data, and that data was used to predict these probabilities. So what it's saying is that if this response is low, given that input is low, then the probability of that being 0.964. So we developed this conditional probability map and then use that knowledge to sort of go back and say what would be the status of the input X and S's in this case. So I think a lot of statistical work like given here, this concept here is just saying is that if I observe output y1, y12, y2, and they are all low, what is the probability that the input is low? And then you can calculate that number. And based on that, so when you observe y, you can say whether x is low or x is high, if it is just only two outcome kind of process. And so here in this case, it shows that you can develop a control chart which shows that if it is everything normal, control chart will behave, and these are plotted for inputs only, not output only. As I told, conventional control chart, output is only monitored. In this approach, we are able to get input data from the output observed data and develop the control chart for those. So this is normal process. And now if we create, now you can extend, somebody can say, why you just took 2 stage high and low? Well, you can have more stages, high and low, but it still can be done that way too. Okay, and this particular slide is showing that if there is a fault in system, something has happened to the input. How do we monitor? Well, because we can plot, Bayesian network gives us the input information, we can plot these charts, x11 setting s11, input x21 and setting s21. We can see that from this, that something is wrong in the output, as we saw here. But input tells me that out of these 4, this is the input where the fault has occurred. And we can even see what time it has happened, because based on the samples, we know exactly when this has happened. So this is very useful knowledge as we try to build the control charting algorithm for the input based on observed data, which is output. Now, I just summarize this here and trying to show that what steps we use. We take the data, we calculate, essentially the behavior of the data in terms of normality. We develop controls, Bayesian network based on this stage modeling, and then from network we simplify the network. Then we observe the output from the observed data, which is responses, and then from responses we get back to the input data, and then we chart control. We develop a control chart for the input, and then try to diagnose the problems. Now, I don't have time for here, but what we did then later after this, we used this hard embossing process. We built a setup, and we created 2-stage hard embossing process, and then we developed this whole Bayesian approach to model it, then simulated the abnormal behavior of the hard embossing process at every stage, tried to see how it works. And this work was done internally at the University of Illinois, then Intel essentially has taken this and implemented using, some software, internal software, and also the student who worked on this project, Intel has hired to really see how this particular program can be implemented in Intel. So that's one way of really taking this thing research from the research lab to the company. Because the student is in the best position to really translate the work. Okay.
Thank you so much. Let's thank Professor Kapoor, who is always able to explain a very difficult concept in an elegant and understandable way. Professor Gore said he had a question.
Actually, long back, 40 years back, we had a similar problem from ordnance factory down to gun and shell factory. They are producing the shells, and a lot of material were being wasted because of the mismatch of dimensions, etc. And we were asked to find out where it is happening, at which stage. So it's very interesting that more or less, of course, we didn't do it in so sophisticated a manner. But one thing we noticed that where a defect is there in the machine or fixture or guide, it was a systematic error and we could identify it. But there are certain errors which are not identifiable because you don't get a curve like that, but you get a flat. So in such cases, what do you do?
Probabilistically, you can predict those things. Okay, it's very clear if it is systematic, you can predict that. But if suppose, you got the error and then it disappear again. It can also a false error, for example.
Which
False
stage
error.
is the problem? That was very difficult
Yeah,
to find.
so cyclic pattern if you have, then you have to basically learn that process. So now this is why machine learning is helping in this. You essentially train the network for these kind of changes.
Now this is a possibility.
Yeah, so now you can train them. And in fact, one of the things which you're talking about, sometimes people say, if I'm developing a new process, I don't have really the data. So that's where the modeling part comes into play. So we can, based on the physics, we can develop a model and then generate data from the model and then train our network that data with all these different scenarios of faults. And then that trained network now use predict that. So
Thank
this
you.
is because of machine learning it is possible to do.
But I think
Let's-
the software will change from product to product.
Product to product, it will, the software basic principle is same.
The actual thing will change.
Actual thing will change because you learn that. And you keep updating that. Learning process is always, I learned it today, then more data comes in there, learn. That's what Google is doing for us, right? We type something and Google gives you something today. This is all AI stuff now.
Let's take another question.
Can it be applied to remaining life assessment of the components or some of the structures?
Apply to who?
Remaining life assessment.
Yeah,
Basic real life.
yeah, definitely. As long as you have data.
So data is to be provided by the organizer.
Right. Exactly.
So is it device based or it is chip based?
It is.
Device based or chip based? Some chip type is they are available or it is just some device is working?
No, device is collecting data for you, right? You collect data, information. Basically, you need information. You can collect directly from the, by interviewing people, for example, you collect data, right? You just interview a lot of experts in the area, you collect data. So data collection can be done in different ways. As long as you have reliable data, it will predict it.
But sir, just I came to know one of my friend is based in Canada. He's working in this system also. He's telling that he has developed some chips. And if the chips are inserted, and then it can...
So there are chips to diagnose. These chips are basically programmed, right? They are essentially programmed to do certain things, certain algorithms. That's what it is. These chips are being, they are trained.
Perhaps these are RFIDs.
It is, a lot of, that's where the intelligence is being put in these chips, basically taking the algorithm, putting in the chips. So computationally it can be efficient.
Thank you. Let's take a last question before we go on to our last speaker for this session.
So I have a very small question. That approach, it requires a large amount of data or small amount of data that
Good question, very good question. More data you have, better results you are going to
But
get.
we can apply for small data also.
Yeah, so this hard and passing process, we developed in the lab. We can collect million data, right? We can only collect a few small data sets. It works, but certainly, probabilistically, more data you have, better results you'll see. Yeah, I can get 1,000 data points. That's what we did here. But if you have 10,000 data points, this algorithm will be more accurate. But it is possible. That's why we also emphasize that sometimes it's good to have a model, and then you can vary the parameters of model and create data. So you generate a lot of data using a model. Physically, you don't have to spend money to create data.
Very good. So let's thank Shiv Kapoor again for an excellent talk and good questions. That brings us to our last speaker of this session, and this is our director of the MIT Johannesburg, Professor Gupta. You're already, you're so fast.
Thank you, sir. So let me introduce the keynote speaker, Dr. Gautam Sutradhar. He has rich experience in industry. He has worked for 5 years in Hindustan Motor Limited and Indian Railways. He joined as a faculty member at the National Institute of Foundry and Forged Technology, that is the now stated NIAMT Ranchi, in 1991. He later served at Sarampur Textile College and Kalyani Government Engineering College for about 10 years before joining Jadavpur University, Kolkata as a professor in the Department of Mechanical Engineering in 2005. Currently, Dr. Sutradhar is holding the position of director at the National Institute of Technology, Jamshedpur, Jharkhand since May 2023. After successful completion of full term as director, National Institute of Technology, Manipur, Imphal. He has supervised more than 20 MTech thesis and 21 PhD students in the field of metal matrix composites, polymer matrix composites, development of environment-friendly materials, synthesis of post-powder metallurgy components, and metal casting processes. He has authored 2 books. He has published more than 125 technical papers and presented more than 50 technical papers. He recently has been awarded as the long-standing contribution to IIF Eastern Region on the eve of National Foundry Day 2023. He is one of the major contributors to the nationally coordinated project under the Make in India initiative in manufacturing technology, that is Smart Foundry 2020, sponsored by DST, New Delhi. I welcome you, sir, on behalf of TRMM 2023, and now the dais is yours.
ये वाला क्लिक करेगा ना? Very good afternoon. Very good afternoon. I am really thankful to Professor P.P. Chattopadhyay, Director of this institute, to invite me for this occasion. I thought that the topic which I want to really share with you, which is related to the manufacturing or industrial scenario. And I thought that the direction which the institutes should focus on for the near future, as well as the industries to focus, because we are a very big country, about 140 crore of population, and each and every year about 1.2 crore graduate students are trying to get the job. So there is a huge task on manufacturing is definitely there. So to start with, I thought I should give something which is almost last 400 years almost, because we have got our independence almost 70 years, but we could not develop our GDP, which was at that time around 12%. It is around 16% now. We could not. So I want to find out what is the reasons behind it. Why we could not improve our GDP in manufacturing. So my presentation will give you some idea, the background of this thing, why we could not improve our GDP. See, prior to the British rule, we Indians have a very independent economy, and it was primarily based on the agriculture. Other than this, India is very much well known for different type of cottage industries like metals, precision stone carving, cotton textiles, silk textiles, and this cottage industry and the products were very much welcome or having huge demand in the rest of the world. During the British rule, when Britishers came to rule our country, they totally tried to deindustrialize of India systematically. They make this thing, disindustrialization, and very systematically. What they have done, they primarily export the cheap raw materials from the country, and they put the finished goods in their country, and that same finished goods are coming to our country. As a result, what happened? Their industries were much better position. Industrial situation was much better position. Not only that, when India at the time is sending or exporting the raw materials, almost free excise duty. When the finished good is coming, free excise duty. But when India is sending their industry goods, it is a high excise duty. That means from the very beginning, they tried to just exploit India, and they ultimately, our industrial growth is almost getting restricted. After that, when the British rule started, they started few industries which they really interested. Only port trust, power sectors, railways and post and telegraphs. Now, in the second half of the 19th century, India slowly established some modern industries which primarily jute and textile. Jute is, they have concentrated on the eastern part of India, West Bengal, and textile, they concentrated on the western part of the country. And they, at that time, first iron and steel company has been started in 1907. However, the production started in 1912 under the leadership of Jamsetji Tata. This production of Tisco, when it started, at that time, other industries slowly coming up. Those industries are cement, sugar, paper, and chemical and other related industries. After setting up of that steel plant in Jamshedpur and also nearing to the Second World War. Now, when the independence we got in 1947, after that, it is seen that our GDP is 11.8% only, and total infrastructure in manufacturing and industrial scenario is very, very pathetic condition. And then India thought to make 5-year plans, you know. During the second 5-year plan, that means almost 1956 to 60, 62 like that, at that time, India had taken 3 policies, very important policies, to develop their infrastructure. Number 1 is the industries which will be exclusively under the state government, like petroleum, coal, aviation, steel, they are restricted to the state. Other category industries are private sectors, but these industries again monitored by the state government are under different issues for the quality control, license and other things. Third category is again private sector, but that sector is also under some point of time, they are actually controlled by the again state government. Now, as a result, what happened? We have seen in the last part of the 20th century, that means 1975 to 1990 or 2000. At that time, we find that the manufacturing scenario is not very good. At that time, China becomes the factory of the world. And we are lagging behind because of many issues, particularly infrastructure. Now the thing is that in first jump, quantum jump, at least Indian scenario for the industry started in 2014, when a policy named as Make in India and having 3 major important key points is there in this Make in India program. First one is the simplification of the business, that means ease of doing business. Number 2 is that infrastructure development, including first forwarding the delivery and industrial corridors. And third is the opening up of new sectors for growth, particularly a foreign investment in railways and defense from the some accord. Now we know that we are at present moment we are moving with fourth industrial revolution. Fourth industrial revolution was started at the, everybody knows that it is from the steam engine, that invention of steam engine, steam power plant. And after that, second revolution was for the electricity, and which was done at the second half of the 19th century, where it is required for the mass production. And ultimately, third phase, which is basically on the outsourcing of production, low labor cost, at the time destination of China and Thailand emerging as a manufacturing powerhouses. Now, this paradigm shift, which is actually tuned in 21st century, is driven by the Industry 4.0. We all know this 4.0 is basically a collection of 9 cyber physical and data technologies, and Industry 4.0 is the fourth manufacturing evolution since the development of the steam engine. Now, here the main part is that if we just thoroughly see the Industry 4.0, you will see that there are 3 major structural shifts are there. What are those? Now, first structural shift in 4.0 rather than previous, that industrial robots. Industrial robots were used before 4.0 also, but the new robots which are used in 4.0, they are more intelligent and they are more trainable, and they are working with artificial intelligence, in their activities. And then second structural shift in 4.20, which means the growth of global digital service. Now the digital services started, and these digital services are becoming more growth and more profitable than the manufacturing even companies for that, because these digital services are becoming more profitable. And third structural shift seen when there is a growth of digital trading platform. When the digital trading platform is used as a platform for selling, and this transformation of global supply and traditional country-based business models become redundant. For example, Chinese mobile phone company entered India by emerging one such platform and did so more quickly with much less investment than one its companies. So this is the third shift which has been found in the Industry 4.0. Then after that, at the time one very important thing is being noticed, that small companies find it more easy to compete with the global market because of this digital service. Now we are thinking for Industry 5.0, which may be the future industrial scenario. This fifth industrial revolution focuses mainly on men and machines can work together, and based on the personalization and the use of the collaborative robots, workers and free to driver deliver value added tasks for the customers. The latest iteration goes beyond the manufacturing process to include increase in resilience, human-centric approach, and a focus on the sustainability. Now, the future before going to the future, now I am telling you the recent developments for the Indian industry. In NASCOM recently said that India is really captured about 20% of the IoT market, which is projected about $300 billion by 2020, with the implementation of massive amount of IoT applications. However, it would be possible only providing very high-speed data connectivity system. Considering these factors, Government of India launched the Bharat 6G Vision document in 2023 March to make in India a frontline contributor of 6G technology and manufacturing by 2030. This document also accepted by the International Telecommunication Union. Now, the global manufacturing sector is undertaking a massive structural transformations, and Make in India 2.0 must enable us to retool our manufacturing for the digitally driven future. India has time to get its right time in this time, and every new manufacturing technology in the past took about the several decades to mature. Under this dynamic leadership of our Honorable Prime Minister Sri Narendra Modi ji, the Government of India launched India Semiconductor Mission that aims to build a vibrant semiconductor and display ecosystem to enable emergence as a global hub for electronics and manufacturing and design, so that the new India becomes Atmanirbhar Bharat. The global semiconductor market size is estimated about USD 990 billion by 2030. At present, USA, China, South Korea and Japan dominating the whole market, semiconductor market. And India is emerged as the largest ecosystem for the startups, and this startup globally, as per the report on 31st May 2023, India becomes a 108 unicorns with a total valuation of $340 billion. And also India becomes the second largest mobile phone manufacturer in the world. So therefore, it could be concluded that let us join hands in hand to achieve the aspiration of New India in line with the visionary statement of Honorable Prime Minister, as I quote, "In last century, Germany and other countries took the benefit from the Industrial Revolution. India was a slave back at the time. It could not leverage benefits. India will not be left behind in the fourth Industrial Revolution, and it is leading the world." So thank you very much. Jai Hind, Jai Bharat. Please.
Yeah, if there are questions.
So this was, for me, very informative, and I would like to share the summary slide with my friends in Mexico to see how they will tackle the same kind of problems they are facing. So thank you. So we have some time for some questions. I see Shiv is eager. Steve's in here. Yes, there we go.
Sir, this was a very nice presentation. This is one of the nice presentation, very much eye-opening to many of us. So I will just ask one question regarding this. Sir, regarding this, can I ask that is there any environmental concerns regarding all these things?
See, environment is always concerned. As you know, the industrialization is going under the opposite direction. It's not, but today I think you have heard the lecture of Professor Ghosh. What he told that CO2 can be converted into oxygens. You have to, some methods is expecting that 30 to 40 years. So some such mechanism will come that with the industrialization, it will not be the, it will not hamper any environmental issues because of again converting the CO2 to, yes. So at that time I think that that issue will come as he has already predicted.
Any other question? Yes, in the back there's a question.
Thank you, sir. I have one small type of things that you have stated after Industry 4.0, but the micro-industry concept you have discussed earlier in the time of before the independence, there were small-scale industry. You have cited about that. Now, those industry, particularly some of the industry which were running more than thousands of years back, like wrought iron steel industry, ancient iron making furnace. So these are almost extincted. So this type of microeconomy, micro industry can be revived, or whatever it is already many types of the such type of the micro industry which are not working till date. So how to revive those things for the improving our Indian economy?
Yes.
For tribals and rural peoples.
I just telling one example. It is not abolished. I could not Netarhat, near Netarhat there is one small village is there. At this moment I could not know. I do not recollect the name.
Gramin Vikas technique.
Huh?
Gramin Vikas.
No, there is some villages there in Netarhat near about, and they are still maintaining the process of iron making what they have done 1000 years before what you are telling. And one small project we have taken from the Jamshedpur NIT under the Sachata Bharat or something, some scheme.
Yes.
We got some small amount of money to make them aware, because they are doing as their forefathers are doing, okay? And the similar process they are doing. Whether it is economically viable or not, they do not have any idea. They are doing making. So we are trying to interact those community so that they could make it more efficient and more economic way. We have already taken this project. If you are very interested on that, I can give you the name of the coordinator. He is going, and many people who are coming to Jamshedpur NIT,
yes,
they are also going there to see the iron making process. I have seen the photographs. I have not gone there, but still they are making. They are making the different type of one just small kind of swords. They are still making. Okay, and I don't know, and it is not even corroded.
Yes, yes, yes.
A very peculiar type steel they are making by their own small furnace. Okay, so that is still there. I am not very thorough about the program which is going on, but it is still going on.
Actually,
Yes, sir.
Madhya Pradesh government has produced a movie on that, because they have actually shown the whole process through which in Madhya Pradesh, in many villages and rural and forest areas, similar kind of steel is being made,
Achha.
or iron, and they have produced a movie. That movie is available with NITTT at Bhopal.
Okay. But sir, this Netarhat village, that project is going on. I will give you the name who is coordinating that.
Yes.
Okay, and many people are going to visit there and try to make how that can be improved.
Yes, sir. I have also done the PhD thesis on this, improving the quality of iron and productivity and yield of iron. Working at National Metallurgical Laboratory, Jamshedpur. It has been improved substantially from 20 to 25% to 71% by using different type of the charcoal and this with a very less expenditure of the money, which will be helpful to improve the microeconomy of the rural population.
Yes.
So I want some help, some guidance from you to.
Okay, I will just talk after
you.
that. Okay, I will just give the particular person who is doing on that project.
Yes.
Okay. Thank you. Anybody else?
Did you bring your wallet? Did you bring your wallet?
Good afternoon, sir. Sir, is GDP exactly a reflection of Indian economy or any loophole behind this or any limitation of GDP? Can we find out the Indian economy through the GDP?
See, at present you know that service sector, at this 5 years back, service sector GDP was 56, 59, 59 like that. Now it is 53% or 54% like that. Because service sector definitely grow, but my perception is that industry GDP contribution is about 30, not more than that. In manufacturing now it is even 15 to 16. So basic, what I find that the main problem is that with the rest of the world, we could not progress, particularly 1950 to 2000. We could not, we tried, but at that time our population growth is very high, no? And that is why we could not do the sustainable thing. But if you see the statistics, you will see that after 2014, that Make in India program, local for focal, the Startup India, these things basically little GDP growth changes. Our target was 25 in manufacturing, at least by 2030. But for that, the semiconductor जो manufacturing and design जो अभी just शुरू हुआ रहा है, okay, and definitely we will take on that because what I have already discussed, no? During this thing, this 4.0, if you go to improve, you have to make the other things also. Say 6G concept, then semiconductor, then other relevant infrastructure to improve. So you improve then only. Even I have seen some government notice, some notification that if we really grow in this manner, then only possible 12 million literate graduate engineers or diploma holders per year. It is then only possible to employ. Okay, so this is very important issue. That is why I thought it should be aware not only for the students but also to the industries, to the academicians, which area we should focus, which area will focus. We have to train the students in that area only, we have to focus area, show that our total GDP can be improved. Okay, thank you very much.
Thank you very much. Let's thank our speaker again. Thank you.
So thank you, and I request Director Sir to thank Professor Mark Meadow and give a token of appreciation from the Institute. Thank you, sir, for chairing the session. Please have a big round of applause for Mark Meadow, sir. So we are going to have a break of 15 minutes. Yeah. So I request all of you to proceed for the tea break. Just at the entrance of the auditorium, the tea is organized. So you can take tea and come back at 5 for the next session, which is going to be online. And the first lecture is going to be from Dr. Kishora Shetty. Boeing. Yep. Thank you.
हो गया टी वाला